So when we actually do find E, it's just going to be a big polynomial.
Well, this is as long as it gets. I mean, this is a generic example. If I'm not sure what you're asking about.
It's just going to be one function.
Well, if E exists, it's one function. Yes. So let's do an example of that. Let's show you randomization. Make sure. Okay, now that has the answer. So, are you willing to repeat this exercise? So now let's see how a problem can be possibly solved. How can you actually find the function? All right, I'm ready.
Minus 2x squared minus 2y squared plus b squared plus 2xy plus 2yz minus 6xy, comma, x squared plus 2y squared minus 2b squared minus 4xz or xy, sorry, minus 6yz plus 2xz, comma, minus 3x squared minus 3y squared plus b squared plus 2xy minus 4yz plus 2xz.
All right, thank you very much. Okay, well, the process is the same, right? If the function exists, its gradient is computed like that, must be equal to this f. So we have a system. Well, let me, instead of rewriting again, you have it in front of you. So let me do the antiderivatives. Is it okay if I don't rewrite again that stuff over here? Well, then I anti-differentiate this first component with respect to x. So let's do that. It's minus 2/3 x cubed minus 2xy squared plus xz squared plus x squared y plus 2xyz minus 3x squared z. Alright, now the second line should be integrated with respect to y. So I need y, x squared y. Is there x squared y here? Yes. X squared y. And then 2/3 y cubed. No such thing there. Well, sorry, I forgot the first constant. Constant with respect to y and z. Now the term 2/3 y cubed doesn't show up in the first equation. I put it on the side. Integral of minus 2z squared with respect to y is negative 2yz squared. I don't see such thing there in the first. So negative 2yz squared. Antiderivative of negative 4xy with respect to y is negative 2xy squared. Negative 2xy squared matches something I have already. Antiderivative of this with respect to y is negative 3y squared z. Negative 3y squared z. There is nothing in the first equation to match. And finally, integral of this with respect to y, 2xyz. It's right here in the first equation, plus 2xyz. So you see now that the two equations match much better than in the first case. Now let's check that these extra terms can actually be hidden in the C1. Can they? Do you see that? All these are in terms of y and z only. Now, we can do the same thing, it's the same kind of checking for the second equation. The constant here is C2 of x and z. And the question is, are those terms you see in the first equation that have no match in the second? So this term, and that term. Are those three terms hidden or can possibly be hidden there? Yes. Alright, so now we have match of the first and second equation. The third equation, integral of the third with respect to z. So minus 3x squared z. It's there. Minus 3x squared z. Now, minus 3y squared z. It's there. Minus 3y squared z. The next one. Integral of z squared with respect to z. It's 1/3 of z cubed. It never showed up before. And integral of 2xy with respect to z is 2xyz. That term is there. Integral of negative 4yz with respect to z is negative 2yz squared. Negative 2yz squared. It's right there. Negative 2yz squared. And finally, integral of 2xz with respect to z is xz squared. Xz squared, right there. And of course, there is a constant. Plus a constant in terms of x and y. Now, are you ready to write down the function? You just read it off, right? From the whole table you have. So, minus 2/3 x cubed minus 2xy squared plus xz squared plus x squared y plus 2xyz minus 3x squared z. Now plus 2/3 y cubed minus 2yz squared minus 3y squared z plus this 1/3 of z cubed. Are we done? That's right. It is possibly a numerical constant, right? You can add 5 to it, you can add 7 to it, you can subtract 100. Now, how important is that? Well, speaking of potential energy, right? What's the potential energy of this marker? Is it mass times the gravity constant times the height? Height over what? Height over the floor? Height over the table? Height over the ground floor? Well, that's exactly the stuff about that constant, right? You choose that constant by choosing the 0 level for your coordinate system. So that constant we are talking about is about the choice of coordinate system in practice. And yes, there is a constant. Now, mathematically, of course, the function will be different for different constants. Now, the trick here that I have implemented in the problem is that the problem asks for the difference. Well, I don't know how to show you that. Oh, okay. Look, the problem on the WebAssign asks for that difference. My mouse. the difference of two values. So if the answer actually exists, the number you type into WebAssign is going to be the value of this long function at the point -1, 1, -1, right? And you know how to do it on Wolfram Alpha, right? You type it in, say, comma, where x equals -1, y equals 1, z equals -1. So you get that number, and you also evaluate all that at 0, 0, 0, 0. And I really hope you can do it without Wolfram Alpha. And then you subtract those two magical numbers, and that number, what I claim is that that number doesn't depend on how you choose the constant. Right? But basically, you will evaluate all that at some point, and you will subtract the value at 0, which is exactly that constant. The constant will cancel, and it will not show up in. So the physical meaning of that difference is coming from the idea that when you use potential energy, you never use the actual value of the potential energy at the given point. Nobody cares of what exactly the value is at this point. What you actually use is what the difference is between potential energy here and potential energy here. Right? That's exactly what matters. And that's why I use this difference. So the difference is independent on the choice of the constant. Alright, so basically this is how long the solution is. I never tried to work out these steps on Wolfram Alpha. I don't know how quickly and how effectively you can do it. What I would suggest for the purpose of the test is to use a table. If you work with a Google Doc, there is an option of inserting a table there. And well, you can imagine that if you do this operation by hand and you type consecutively all these terms, and then you begin typing all these terms in the next line, well, you will have a hard time matching things and noticing. So what I suggest is that you use table. You make a table with 3 rows and 10 columns or something, and you put these terms in that table. So sort of the way I did here. You see this beautiful table? Now this is the way you will see the file online. The problem is that this table tries to bring this 2xy squared term. It brings x to the next line and y squared to the next line because the column is too narrow. Right? So to see that better, you zoom in to the web page. It is Ctrl+ on the Macintosh computer. It's whatever it is on Windows. I don't know what the keyboard key is. But if you zoom in, at least if you well, unfortunately, this might not work in the So, well, it might not work in this second Windows setup that I have currently. So if you have it in main window and you have only one screen, just zooming in will make that formula look nice. Alright, so that's the end of it. You get the function, evaluate, subtract two numbers, you're done. And the whole solution is actually, well, this is what you copy-paste from the website, from the WebAssign. Well, this is basically a copy of that, right? This is what you do, and you can do it by hand. You type in these 3 lines, and you either have a function that matches the whole thing, or you figure out 2 differences and show me the contradiction. Any questions? Yes.
So it's the same for two-dimensional?
It is exactly the same for two-dimensional. Instead of 3 functions, you will have 2. Right? Instead of matching 3 lines, you will have to match 2. Instead of a constant being a function of 2 variables, you will have a constant being a function of 1. So, let me repeat the question then. Should I do a problem with 2 variables then? Wouldn't you consider that very similar, even simpler than what I have? Alright, so are we done with this topic? So it's basically about this computational ability and understanding how to find antiderivative. And now you can see that if you choose the functions randomly, it is very unlikely that you will be able to match all those. So for random vector field, it is not a gradient of any function. And well, I will return to that later in different context, in the context of potential energy of vector field of forces.